Hello friends, myself Dr. Nandakumar Rao Bawali from College of Engineering Ambazogai is going to deal with Applied Thermodynamics 1. This is our 13th lecture concerned to Applied Thermodynamics 1. In previous class, we have discussed about the fuels, then sources of energy, classification of fuels, and calorific value of fuel, higher calorific value and lower calorific value of fuel, and determination of calorific value of fuel. Today we will discuss about combustion equations, analysis of combustion equation by mass, and analysis of combustion equation by volume. So today we will see the combustion process and how these combustion equations are formed. Generally, in a combustion process, combustion is said to be complete when the fuel is completely oxidized. Elements of fuel are completely converted to their oxides. For example, carbon in fuel is burned to carbon dioxide, hydrogen is converted to water vapor, and sulfur is burned to sulfur dioxide along with the production of heat. If the combustion process is incomplete, the hydrogen and sulfur usually burn to completely while a part of carbon burns to carbon monoxide and rest to carbon dioxide. With incomplete combustion, heat evolved during the process is less than the amount of heat which is to be liberated by the complete combustion of fuel. For the purpose of combustion chemistry is to determine the air required for combustion and finding out the products of combustion quantity. The combustion reaction is written in the form of a chemical equation expressing the conservation of mass in terms of conservation of atoms. For complete combustion of carbon in a fuel, the equation is written as carbon plus oxygen, that is C plus O2 produces carbon dioxide plus heat. So the above equation means that one molecule of carbon reacts with one molecule of oxygen to produce one molecule of carbon dioxide along with the generation of heat. The quantity of heat may not be written every time. The amount of oxygen given by the above equation is just enough for complete combustion of carbon. Such a balanced equation with the minimum oxygen requirements is called Psychometric equation. Since the oxygen for combustion is invariably supplied from air, the stoichiometric equation is useful to determine the theoretical or minimum quantity of air required for combustion. It may be noted that the number of carbon and oxygen atoms are the same before and after reaction. The minimum quantity of air needed for complete combustion of fuel is known as a stoichiometric air. The above equation can be interpreted in different ways, as first one is A, on molar basis. On molar basis, 1 mole of carbon combines or burns in presence of 1 mole of oxygen to form 1 mole of carbon dioxide. It is to be noted that moles before and after reaction are different. That is, moles are not conserved during the combustion. That means 1 mole of carbon burns in presence of 1 mole of oxygen, and the resultant is also 1 mole. That means here actually it is not going to become 1 mole plus 1 mole as 2 moles of carbon dioxide. That is nothing but the mole is not conserved. And second one is B, on volume basis. One volume of carbon burns in presence of 1 volume of oxygen, thereby producing 1 volume of carbon dioxide. Now here we can see the volume of carbon, as the carbon is in the solid form, is very small in comparison with the volume of oxygen. Volume of carbon in comparison with the volume of oxygen is very small or that is negligible, and hence 1 volume of oxygen with negligible volume of carbon produces 1 volume of carbon dioxide. Again, here it is to be noted that volume are not conserved during the combustion equation. So 1 volume plus 1 volume, it is not going to become 2 volume. That is nothing but volume is also not conserved. So third case, if we see on mass basis, the chemical equation on mole or volume basis can be converted to mass basis by multiplying number of moles or volumes by respective atomic mass. Hence, oxidation of a carbon can be written as 1 carbon into 12 kg, 1 mole into 12 kg of carbon plus 1 mole into 32 kg of oxygen produces 1 mole into molecular weight is 44 kg. 44 kg of carbon dioxide is produced. Thus, the total mass of reactants is nothing but 12 plus 32, that is equal to 44 kg. So coming to the reaction equations, we will look into reaction equations or combustion equations in detail, as the equations of stoichiometric or chemically correct mixtures are classified into various categories. So very first category that we will be discussing here is 1A, carbon burning to carbon dioxide carbon burning to carbon dioxide, that is CO2. This analysis is made on mass basis, analysis by mass. Analysis by mass. So in this first we will see carbon C burns in presence of oxygen O2, thereby producing CO2. Then substituting the values of molecular mass, substituting the values of molecular mass. Molecular masses or mass. So here 12 units of carbon, 12 units of carbon, 12 units of carbon by mass, react with 2 into 16 units. 16 is the molecular mass, units by mass, units of oxygen by mass, producing 44 units of carbon dioxide by mass. Therefore, we can write here this as 12 kg of C means carbon plus 32 kg of 2 into 16 is 32 kg of oxygen O2 produces 44 kg of CO2. That is nothing but dividing above equation, say we say this as chemical equation 1. Dividing above equation by 12, we get 1 kg of carbon is burned in presence of 32 divided by 12 kg of oxygen to produce 44 divided by 12 kg of CO2. That is nothing but on simplification 1 kg of carbon is burnt to produce 8 by 3, 4 3s are 12, 4 8s are 32, 8 by 3 kg of oxygen produces 11 by 3 kg of carbon dioxide on combustion. So here what we can say is 1 kg of carbon requires 8 by 3 kg of oxygen to produce 11 by 3 kg of carbon dioxide. So we can say this as equation number 2. Coming to the next aspect, 1b. So here carbon burning to carbon dioxide, and this analysis is made on the mass basis. Same analysis we will be doing with the volume analysis, and that we call it as 1b. This is 1a. Now we will move to 1b, and in 1b we will be discussing about the volume analysis. So in this volume analysis, we write here 1b, carbon burning to carbon dioxide. Carbon dioxide analysis by volume. So here we write the equation. Carbon burns in presence of oxygen to produce carbon dioxide. Now, by Avogadro's hypothesis, the molecule of all the gases occupy same volume under the same conditions of temperature and pressure. Therefore, negligible volume of solid carbon plus 1 volume of oxygen produces 1 volume of carbon dioxide. So that we write here 1 volume of, or negligible volume of, solid carbon plus 1 volume of oxygen produces 1 volume of carbon dioxide. Because the volume of solid is very negligible in comparison with the oxygen. Therefore, here also we can say that the volume is conserved. Now coming to second A, carbon burning to carbon monoxide. Carbon monoxide. Carbon monoxide. And this analysis is again made by analysis by mass or mass basis. Now here the carbon monoxide is produced by incomplete combustion of carbon. So if carbon burns to complete carbon dioxide or complete combustion of carbon, whenever occurs, it produces carbon dioxide. So if the carbon burns to incomplete combustion, then produces carbon monoxide. So 2 moles of carbon combined with 1 mole of oxygen producing 2 moles of carbon monoxide. So here on the mass basis, if we see 2 into molecular mass of carbon is 12, 2 into 12 kg of carbon combines with 2 into 16 kg of oxygen. So here we have the mass of oxygen as 32, produces 2 into carbon monoxide. The molecular mass of carbon monoxide is 2 plus 16 kg of CO carbon monoxide. On simplification, we get this 24 kg of carbon combines with 32 kg of oxygen, producing that it produces 12 plus 16, 18, 28, 28 into 2, 36 kg of carbon monoxide, kg of. So dividing this equation by 24 throughout, we get 1 kg of carbon burns in presence of 32 divided by 24 kg of oxygen to produce 56 divided by 24 kg of carbon monoxide. On further simplification, this we can write as 1 kg of carbon is burned in presence of 4 by 3 kg of oxygen. So 8 3s are 24, 8 4s are 32, 4 by 3 kg of oxygen, and this is nothing but 7 by 3. 8 3s are 24, 8 7s are 56, 7 by 3 kg of carbon monoxide. We can write this as equation number 3. When 1 kg of carbon is burned in presence of 4 by 3 kg of oxygen, produces 7 by 3 kg of carbon monoxide along with the heat. So then we'll go for second B. This is second A. Carbon burning to carbon monoxide. The analysis is made on the mass basis. So now carbon burning to carbon monoxide analysis made on volume basis. We will discuss. To B. Carbon burning to carbon monoxide. Carbon burning to carbon monoxide and analysis is made on volume basis, analysis by volume. So here 2 moles of carbon are burned in presence of oxygen. 1 mole of oxygen produces 2 moles of carbon monoxide. So 1 volume of oxygen combines with carbon of negligible volume and produces 2 volumes of carbon monoxide. So here this is negligible volume, here the negligible volume of carbon volume of fuel, carbon, solid fuel, burns in presence of 1 volume of oxygen and produces 2 volumes of carbon monoxide. Coming to the third equation, third A, carbon monoxide. Now first carbon is burned to carbon dioxide, then carbon is burned to carbon monoxide. Now carbon monoxide is burned into carbon dioxide on mass basis and on volume basis. We will be looking at the analysis. So A, carbon monoxide burning to carbon dioxide carbon monoxide burning to carbon dioxide, and this analysis is made on analysis is made on analysis by mass. Now here 2 moles of carbon monoxide are burned in presence of 1 mole of oxygen, thereby producing 2 moles of carbon dioxide. 2 into molecular mass of carbon monoxide is 28. 16 plus 12 of carbon monoxide of CO plus 32 kg of oxygen O2 produce 2 into 44 kg of carbon monoxide. That is nothing but 2 into 28, 36 kg of carbon monoxide, 32 kg of oxygen produces 88 kg of carbon monoxide. Dividing this complete equation by 56, we get 1 kg of carbon monoxide is burned in presence of 32 divided by 56 kg of oxygen, producing 88 divided by 56 kg of carbon monoxide. On further simplification, we get this as 1 kg of carbon monoxide is burned in presence of 4 by 7 kg of oxygen, producing 11 by 7 kg of carbon dioxide. This produces carbon dioxide. So this is equation number say 4. So this is carbon monoxide burning to carbon dioxide. This analysis is made on mass basis. So again 3b, the analysis of carbon monoxide burning to carbon dioxide on volume basis. 3b, carbon monoxide burning to carbon dioxide this analysis is made on analysis by mass, volume. Now here 2 moles of carbon monoxide are burned in presence of 1 mole of oxygen, producing 2 moles of carbon dioxide. So 2 volumes of carbon monoxide are burned in presence of 1 volume of oxygen to produce 2 volumes of carbon dioxide. So now coming to the next constituent of fuel, that is known as sulfur. So combustion of sulfur, we will see 4a. The sulfur burning to sulfur dioxide, that is analysis by mass. One mole of sulfur burns in presence of 1 mole of oxygen by producing sulfur dioxide. The complete combustion of sulfur produces sulfur dioxide. The molecular mass of sulfur is 32 kg of sulfur burns in presence of 32 kg of oxygen, thereby producing 64 kg of sulfur dioxide. Dividing above equation by 32 throughout, we get 1 kg of sulfur is burned in presence of 1 kg of oxygen, producing 2 kg of sulfur dioxide. We can call this as equation number 5. So for complete combustion of 1 kg of sulfur, we need 1 kg of oxygen, that produces 2 kg of sulfur dioxide. And then 4b, sulfur burning to sulfur dioxide, analysis is made on volume basis. So now here sulfur plus oxygen, sulfur burns in presence of oxygen, thereby producing sulfur dioxide. So negligible volume of sulfur volume of sulfur combines with 1 volume of oxygen and produces 1 volume of sulfur dioxide. So now coming to other compositions or constituents of fuel, such as methane, ethylene, we will be looking into the equations. So now fifth A, we'll discuss about fifth A, the combustion of methane. 5A, complete combustion of methane. Combustion of methane, that is CH4, on mass basis, that is analysis by mass. Now you can see here CH4 methane burns in presence of 2 moles of oxygen produces carbon dioxide plus 2 moles of water H2O. So here 16 kg of CH4 is burned in presence of 64 kg of 32 into 2, 64 kg of oxygen producing 44 kg of CO2 plus 36 kg of 36 kg of H2O, that is water. Dividing complete equation by 16, we get 1 kg of methane is burned in presence of 64 divided by 16 kg of oxygen producing 44 divided by 16 kg of carbon dioxide plus 36 divided by 16 kg of water. On further simplification, the 1 kg of methane is burned in presence of 4 kg of 16 4 the 64 4 kg of oxygen producing 11 by 4 4 11s are 44 4 4s are 16 11 by 4 kg of carbon dioxide plus 9 by 4 kg of H2O water. We can write this as equation number 6. So this is the analysis by mass. Now coming to the complete combustion of methane, analysis by volume 5b. Complete combustion of methane, that is CH4, analysis by volume. So here we can write methane burns in presence of 2 moles of oxygen producing 1 mole of carbon dioxide plus 2 moles of water, that is 1 volume of methane. 1 volume of methane CH4 burns in presence of 2 volumes of oxygen producing 1 volume of carbon dioxide and 2 volumes of water, that is H2O, in the form of steam. This will be in form of steam. So now coming to next equation, combustion of ethylene, complete combustion of ethylene on the mass basis. There are many more organic compounds which are going to burn in presence of oxygen to produce certain byproducts. So we'll take one more example of ethylene, combustion of ethylene. And then after that we will be moving towards conversion of gravimetric analysis to volumetric and vice versa. So now sixth A. Complete combustion of ethylene. Complete combustion of ethylene. That is C2H4. Analysis by mass. So C2H4 burns completely in presence of 3 moles of oxygen, thereby producing 2 moles of carbon dioxide plus 2 moles of water along with the heat. 28 kg of this molecular mass of ethylene is 28 kg of ethylene C2H4 is burned in presence of 3 moles of oxygen, that is 96 kg of oxygen, which produces 88 kg of 88 kg of CO2 and 36 kg of H2O water, that is steam. So dividing above equation completely by 28, we get 1 kg of ethylene is burned in presence of 2 divided by 7, 96 divided by 28 kg of oxygen, producing 88 divided by 28 kg of carbon dioxide plus 36 divided by 28 kg of water H2O in the form of steam. So this can be further written as 1 kg of ethylene is burnt in presence of 4 7s are 28, 4 2 the 8, 4 4 the 16, 24 by 7 kg of oxygen produces 22 divided by 7 kg of carbon dioxide plus 9 by 7 kg of water, that is steam. So this is the analysis made on mass basis. So we can say this as equation number 7. Last equation for today's lecture, that is 6b. Complete combustion of ethylene that is C2H4 analysis by volume. C2H4 is burned in presence of 3 moles of oxygen by producing 2 moles of carbon dioxide and 2 moles of water H2O, that is nothing but 1 volume of ethylene C2H4 is burned in presence of 3 volumes of oxygen, producing 2 volumes of carbon dioxide and 2 volumes of water H2O, that is steam. So these are the important equations for making the analysis of flue gases and the conversion of gravimetric analysis to volumetric analysis and vice versa. That is, the mass analysis is converted into volumetric analysis and volumetric analysis is into mass analysis. That we will be looking into detail in next lecture. So hope that you have followed these equations, and these equations play a very important role for conversion of gravimetric analysis to volumetric and vice versa. Therefore, remember these equations. So these equations signify that how much of oxygen is required for complete combustion of unit mass of the fuel or constituent of fuel is indicated or is highlighted in these equations. So for example, you can see here 1 kg of ethylene requires 24/7 kg of oxygen for its complete combustion. So this quantity of oxygen required is helpful to find out the minimum quantity of air required for combustion of fuel. So air contains oxygen, and the percentage of oxygen in air by mass and volume is known to us, and depending on the percentage of oxygen present in the air, we can find out the quantity of air required for complete combustion of fuel consisting of certain constituents. If the constituents of fuel are known, then we can find out the actual amount of air required for complete combustion. Thank you.